This lecture discusses the methods for estimating a population mean, including point estimation and a confidence interval. A common problem in statistics is to obtain information about the mean of a population. For example, we might want to know the mean age of people in the civilian labor force, the mean cost of a wedding, the mean gas mileage of a new model car, the mean starting salary of liberal arts graduates. In many scenarios, it is impractical to collect information from the whole population. For example, if we want to know the mean age of people in the civilian labor force, the population contains all workers in the country. It is expensive and unrealistic to collect information from everyone. In practice, we draw a sample and use the sample to infer the whole population. Recall that this is exactly how statistics works. In this lecture, we will introduce two influential methods, point estimation and confidence interval. A point estimate of a parameter is the value of a statistic used to estimate the parameter. Recall that a statistic is a number calculated from a sample. For example, the sample mean is a statistic. A parameter is a number characterizing a population. The population mean is a parameter. Because we do not have information for every individual in the population mean is unknown. What is available to us is a sample. We can always calculate a sample mean. A natural idea is that the sample mean is close to the population mean if the sample is representative. This explains that the sample mean is a point estimate of the population mean. Let's summarize it. In order to find a point estimate, we first need to identify the population. Next, we need to take a sample. Compute the sample mean x bar and use it to estimate the population mean mu. Right now, we discuss the point estimate of the population mean. Later, we will discuss point estimates of other parameters. For example, point estimate of the population standard deviation. Let's look at an example. The US Census Bureau publishes annual price figures for new mobile homes. The figures are obtained from sampling, not from a census. In this problem, the population contains all new mobile homes. The parameter that we are interested in is the mean price of new mobile homes. The data contains the prices of a simple random sample of 36 new mobile homes. The prices are shown in thousands of dollars. We can calculate the sample mean from the data. The sample mean x bar is the sum of the numbers divided by the sample size 36. The sample mean is $63.28 thousand. We conclude that we estimate the mean price of new mobile homes to be approximately $33,280. This example shows how to estimate the population mean using a sample mean. Let's discuss some properties of point estimate. A statistic is called an unbiased estimate of a parameter if the mean of all its possible values equals the parameter. Recall that a statistic has a sampling distribution. We have discussed sampling distribution before. Whenever we draw a sample, we can calculate a statistic. The value of statistics depend on samples. Hence, the statistic is essentially random and it has a distribution. This distribution is called a sampling distribution. Because a statistic is random, we can calculate its mean. We have discussed before that the mean of sample means is mu, the population mean. According to the definition, The sample mean is an unbiased estimate. If the mean of the statistic is not equal to the parameter, this statistic is called a biased estimator of the parameter. Of course, an unbiased estimator is usually preferred because it equals the parameter it estimates on average. For a biased estimator, it is systematically larger or smaller than the parameter it estimates. There are also some drawbacks when using a point estimate. Firstly, a sample mean is usually not equal to the population mean due to sampling error. Although it is expected that the sample mean is close to the population mean, they are unlikely to be equal. Secondly, no information is available on the accuracy of the estimate. For example, in the previous slide, we estimated the mean price of new mobile homes to be $63,280. We don't know how accurate this estimate is. Confidence interval is another influential method that incorporates the accuracy of estimation. A confidence interval is an interval. For example, we may say that a confidence interval for mu, the population mean, is interval from 5 to 10. It means that the unknown population mean mu falls somewhere in this interval. When talking about a confidence interval, there is always a quantity called confidence level. This number specifies the confidence we have that the parameter lies in the confidence interval. The confidence level is usually expressed as a percentage. This 95% is a confidence level. When we say confidence interval estimate, we mean confidence level and confidence interval. Usually, we need to find a confidence interval for a given confidence level. Let's look at the example of prices of new mobile homes again. Assume that the population standard deviation of all prices of new mobile homes is $7,200. We can draw a normal probability plot. Recall that this plot is used to check whether the data follow a normal distribution. In this plot, all points roughly fall on a straight line. It indicates that the data follow a normal distribution. It is reasonable to assume that the population is also normal. The sampling distribution of X bar is therefore a normal distribution. We can calculate that the mean of X bar is the population mean mu. Of course, we don't know the value of mu. The standard deviation X bar is the population standard deviation divided by the square root of the sample size. Notice that the sample size is n equals 36. The population standard deviation is 7.2. Therefore, the standard deviation of X bar is 1.2. As a summary, the distribution of X bar is normal with mean mu and standard deviation 1.2. By the empirical rule, approximately 95% of all possible observations lie within two standard deviations to either side of the mean. In terms of mathematics, we know that probability of mu minus 2.4 less than or equal to X bar less than or equal to mu plus 2.4 equals 0.95. Pay attention to the inequality in the parentheses. For the left part, mu minus 2.4 less than or equal to X bar. It is equivalent to mu less than or equal to X bar plus 2.4. Similarly, for the right part, X bar less than or equal to mu plus 2.4, which is equivalent to X bar minus 2.4 less than or equal to mu. Combining these two inequalities together, we have probability of X bar minus 2.4 less than or equal to mu less than or equal to X bar plus 2.4 equals 0.95. This expression means that the interval x bar minus 2.4 to x bar plus 2.4 contains mu with probability 95%. In another word, a 95% confidence interval for mu is x bar minus 2.4 to x bar plus 2.4. Till now, we derived a formula to calculate a 95% confidence interval. After we have a sample, we can calculate the sample mean x bar, replace x bar by the number, and we get the confidence interval. A confidence interval usually has the form of point estimate plus minus margin of error. The margin of error indicates how accurate the guess is as an estimate for the value of the unknown parameter. In the previous slide, the margin of error is 2.4. We have already calculated the sample mean is 63.28. Therefore, the 95% confidence interval for mu is 60.88 to 65.68. The left endpoint is the sample mean minus 2.4, and the right endpoint is the sample mean plus 2.4. We can be 95% confident that the mean price mu of all new mobile homes is somewhere between $60,880 and $65,680. Here, I want to emphasize a little bit more about the interpretation of confidence intervals. We have a population and we can take samples from the population. A different sample will lead to a different value of x bar and therefore a different confidence interval. This diagram shows that we may have many different intervals. Each interval is calculated based on one sample. The confidence level 95% means that 95% of these intervals will contain mu. We may further illustrate it using a simulation. Let's take samples from a normal distribution with mean 65 and standard deviation 7.2. Of course, the true population mean is unknown. Here, for the purpose of simulation, we assume it is equal to 65. We just want to check whether the confidence intervals can contain the population mean. We take 25 samples. Each sample has 36 observations. For each sample, we calculate the sample mean x bar and also construct 95% confidence intervals. Notice that the confidence interval is x bar plus minus 2.4. We can see that most of these confidence intervals contain the true parameter mean 65. Only one interval does not contain 65. 24 out of 25 intervals, or 96% of intervals, contain the true population mean 65. Here, we only take 25 samples. If we increase the number of samples, we will observe that roughly 95% of this confidence interval contain 65. This is the meaning of confidence level 95%.